Hey everybody, this is Larry. This is day 6 of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Poor pigs. Let's see. Okay, the buckets of fun, buckets of liquid, where exactly one of the buckets is poisonous. To figure out which one is poisonous, you feed some number what will they'll die or not. Unfortunately, you have minutes of tests to determine which bucket is poisonous. Okay, this reminds me a bit of the trivia, or not trivia, but a brain teaser that I had when I was a kid. But we'll see if this is the same thing. But yeah, also if you're newish here or whatever, hit the subscribe button to get more content like this. But also, I've been doing an extra bonus question on in my YouTube channel. So definitely, if you hit the subscribe button, you could do an extra problem with me, especially if the problems are with bad. Wow, they're not negative votes. We'll see. Anyway, okay, choose some live pigs to feed. For each pigs, choose which bug is to feed it. The pig will consume all the chosen bugs. Wait for minutes to die. You may not feed any other pigs. Okay. Repeat the process until you run out of time. Okay, let's see. Hey friends, this is a long video, and I don't really have a great short explanation for it. So yeah, so feel free to skip ahead, fast forward, watch it on 2x, whatever you need to do. But the way that I did it for this problem is just by calculating it empirically, by calculating, okay, what is the max number of pigs that we can support in each round, right? Let's say we have 4 rounds, then here, and this is just by an example that if you watch me, then you'll see me kind of go over it as well. Is that okay? Let's say we have 4 rounds with 5 pigs left, right? Then what can we do, right? Well, we can only have one case where all the pigs die. So so all the pigs die. Let's say the pigs are A, B, C, D, E. So you have only one case where that is the case because they're all dead afterwards, so you can only test that once. And then 4 pigs, let's just say A, B, C, D. There's also A, B, C space E, A, B, D, E, A, C, D, E. Basically missing one, right? And there's 5 of these cases. And the idea here, right, is that, well, let's say one of these cases happens. What happened, right? If one of these cases happen, then we are able to support, and there's 3 rounds left, then we're able to support 4 of these, right? Why can we support 4 of these? Let's cut back a little bit. So we have this case. We can support 4 of these because here, let's say, there's 4 scenarios in which A, B, and C, and D drank from these things, and 4 of them died. Well, if 4 of them died, then that means that, and 3 rounds are left, then that means that with 3 rounds left, we have 1 pig, right? 1 pig, 3 rounds left. That means that we can, each of these, if these cases happen, we can still support finding the solution for 4 rounds. This is my point. And what I mean by that, because now let's say you have Y, and we have 4 buckets, then we can just do that last pig, it can have bucket 1, bucket 2, bucket 3, and do 3 rounds, and then either it's bucket 1, 2, or 3, or if the pig survives, then it's the last bucket that we didn't test, right? So that means that with 1 pig left, there's 3 buckets, so we can support 4 additional buckets, and that's why we times it by 4, right? Because that means that we can support 4 of these, because then now we would have these 4, because we know that the answer will have to be one of these 4 buckets, and yeah, and we can support 4 of them with 3 rounds left. So that means that we still have enough pigs for that answer. That's basically the idea. And then the next one, for example, is the 10 cases. I'm not going to draw it out. I'll just draw one of them. Let's just say ABC out of A, B, C, D, E. So you have 10 cases, right? And then in each of these cases, you have 2 pigs left, 3 rounds. And that's basically where the recursion kind of comes from, is that, now we have 2 pigs and 3 rounds. How do you calculate these, right? So and that's where the recursion comes from, and that's where the formula comes from. Is that this is now try in a exhaustive way. Okay, now in the future, in the second round, if there are 2 picks left and has to be how many of these there are that can support it, right? And the 10 cases just means that there are A, B, D. So you're missing C and the E and so forth. So there are 10 of these. So that's why there's 10. And yeah, and for each of these, we can have 2 picks left, 3 rounds, so number of duplicate, because that's how we can differentiate, right? And 2 picks, I don't know the actual number here, but that's basically what I do. So that's basically the idea to calculate the max. And here, the logic is that if we only have 1 round and the upper bound is 1,000, if we only have 1 round, then you can do 1,000 buckets in 10 picks, because it's just 2 to the 10. You have this binary number thing to figure out, and yeah. So in that, I just kind of brute force. Okay, is 1 pick enough? Is 2 picks enough? Is 3 picks enough? Dot all the way until we have enough buckets. And that's basically what I do here. If we have 1 round left and we have X picks, then it's just gonna be 2 to the power of picks, because you could just use the binary number method. Otherwise, if there's no more picks, then you can't test anymore. So there are no more scenarios. So you return 1. Otherwise, you just do this combination thing that we do here. You kill that number of picks, and then you minus 1 round, and then to get the total. You could probably memorize this, but I didn't, and that's fine. But yeah, that's basically the short explanation. You can kind of see me go do this problem next. And it took a long time, but hopefully it was worth it. See ya. Right? So, minutes to die, minutes to test. How does this rounding ever work? Let's see. Right? What I mean by that is, okay, so is this 4 rounds or 5 rounds? Because I guess after 15 minutes, so you have 4 rounds, right? So let's just do rounds is equal to minutes to test over minutes to die. And I assume that, like, for example, if you have 59 rounds, this is going to be round down, because you don't get to feed it, or you don't get to see the result of the thing. Okay, so then now each round, so what happens? Each round you can test minimum number of picks to determine. Okay, so then you have rounds. The idea here, I was gonna say something like, I don't know how I get 5. Minimum number of picks. So okay, so there's 4, in this case, I guess I'm just trying to work out strategy as well. So here, you get only 1 round, and in 1 round you need 2 picks, because it is just the binary numbers, right? Because then now you have 4 buckets. You could label them 0, 1, 2, 3, and for 2 picks, you can, let's say the A and B, you can feed A, this, and then feed B this. So then, or something like that. It doesn't really matter which way you go, because then the idea is that if only pick A dies, then you know that bucket 0 is sad. If both of them die, bucket 1 is sad. If only B is died, then bucket 2 is dead, sad. And otherwise, no one dies, then bucket 3 is the evil one, right? Okay, and then so this is a thing. How do we do it for? So this is what happens if you have 1 round. If you only have 1 round, then it's going to be binary numbers, right? What if you have 2 rounds? Let's think about that for a second. What if 2 rounds? How would you do? Would it just be? Would it, like in this case, the answer kind of gives a hint to my question, which is that can you just, if it's 2 rounds, what happens when you have 2 rounds? I don't know. This is a weird problem for sure. I guess that's why it's a hard, but also a lot of downvotes, because this is maybe a weird one. But I think the rounds is more important than minutes to die and minutes to test. because I don't think, because you cannot feed any pigs during the time anyway. So yeah. Let's see. How would you do 5, right? Well, I'm not going to throw 1,000 buckets, but because I would have guessed. So okay, 2 to the 5th is 32, right? So that's one round. One round. Maybe I could do a binary search if we have a way. And in that case, what would the binary search look like, right? The binary search is that, okay, given X pigs, how many things can we do, right? So maybe we'll do it backwards that way, right? So if we have 5 pigs, and this is just me playing around the number and try to figure out what that means. So let's say we have 5 pigs. For what happens in the first round? Well, in the first 2 to the 5 is 32, right? Let me just confirm that, because I feel like yeah, I feel like sometimes I just get it wrong and it's very tragic. Okay, so 32. And in the second round, or what does that mean? What is the strategy for multi-round? Right. Okay, let's. In the second round, you're not going to do a second 32, right? Is it dynamic programming with the number of pigs dead or something? That'll be a little bit sad. But let's see. I really don't know how to figure out. I mean, I think this is like the brain teaser one. So I'm trying to figure out. Except for that, with the binary numbers, we already can't figure out for 1 round. So now we're trying to figure out for 2 rounds, right? For 2 rounds, and also there is a little bit of a cheating thing, because you can, figure out the answer to get additional examples, if you will. But let's not do that, obviously. Let's say we have 2 rounds. How do you do it? Okay, maybe we'll see if we can figure a pattern to work backwards. Let's say we have 1 pig. What happens, right? Well, 1 pig, you can only test n+1 round or something. Max number. Let's say we have 2 pigs. What is the max number? So in 2 pigs, in 1 round you get 4, right? What happens in 2 rounds? So then here, because it's almost like recursion, I think that's the hard part, is that in this case, none of them are dead. That's good. What happens if A dies? If A dies in the first one, then it's either 0 or 1. So I don't know that this logic is very good for me for now. But okay. But I guess we can just draw it out. Let's pretend does this help this way? Because then the problem is that it's not quite like I cannot do this thing again, right? Because the reason why is because some of these previous one killed some of these other ones, right? So then we have to think about how to encode them such that this is good. Because now it's almost like a recursive thing of, okay, if 1 dies, then what happens? Let's say we have, and we know that, is that true? No, I don't know. I don't know what the number is, but you can imagine that some of them are going to be dead, so that's going to be very sad, right? So let's say, what's the second round? Well, so okay. So I think if at least 1 pig died, then it's one of these, right? But if not, then it's going to be 3, because we know that, or we cannot rule this out anymore, because just because none of them die means that it cannot be 0, 1, or 2, but it has to be 3. And in that case, it's going to be 3, 4, 5, 6, right? Because now we want to test 2 again. And in this case, if we draw the thing, in this case, we're just basically doing it again, but now I mean, you could draw it in any other way, but basically you get a test 4 because we eliminate 3 response. So that means that each round, yeah, and then here, I think this is good for 2 picks, and then yeah, and then with more rounds you do the same, and maybe there's a pattern here, but let me see if that extends to this where you have 4 rounds, right, and 1,000 buckets. Well, in theory, then if you have 5 picks, you have 2 to the 32, but that doesn't even make sense, right? Does it? Because then now you eliminate 32, but then in that case, in theory, you see 31 new picks next time. Is there a way to encode this in a better way? Maybe what I'm doing is not optimal, or it clearly is not optimal, because that would not give us this answer. This would give us 32 times 4 minus 3 or something like that, right? Which is like, you know, a little bit under, like 125 or something, which is obviously not enough for 1,000 buckets. So that we need a different strategy. And I'm sorry that this is gonna be one of those videos that's gonna go a long time, because this is a brain teaser one, and when I do get it, it's gonna be like 2 lines of code, or maybe not 2, but like 5 lines of code without, you know, the ends. Or but hopefully this thought process is good. So, and hopefully if you're still here, you're fast forwarding it or watching on 2x or whatever. So we definitely need a different strategy. And the different strategy is going to be something like, maybe something that's similar to, I don't know if that's true, but like a square root decomposition. So instead of now doing it definitively, now, like almost like we do it for every, okay, so let's say for the other case, right? For the 2 big case, maybe we can, I don't know if this will work, but maybe another strategy will be to repeat, you know, and then let's just see what happens when we repeat it, right? So let's say we have this, and then now we also do this for this, then what, right? Well, then the problem is that, well, we cannot do this because if both of them die, we don't get a round 2. So then now we will eliminate this, for example, or just shift it. So we eliminate this and make this 6. And here, what we can do is that if, you know, if both of them die, is this one. Otherwise, it's going to be either none of them died and it's 0 and 4, or one of them died, it's going to be 1 and 5, or 3 and 6. And then in that case, obviously, you would, you know, use the remaining peg to test, because now you have 2 choices. You have you have 2 choices and 1 peg, or 2 choices with 2 peg, which is also trivial. 2 choices with 2 pegs, and then you could still get 7 that way. Of course, this is not more optimal than before, but maybe it generalizes a little bit better, right? Yeah. Is this some kind of reverse DP thing? Wow. This is a ridiculous problem. I can now understand why there's a lot of downloads. But so then, you know, if you want to generalize this, let's say we have 3 things. So it's 2 to the 8. So now let's say we have ABC, and this is going to be a mess to do. But okay, let's just actually use the binary number. So let's say we have C first, and then we have B, and then you have BC, and then you have AB. Oh no, A. I guess just A, and then AC, and then AB, and then ABC. Right. So this is an 8 thing with 3 pegs. And then now, what would we do, right? If we wanted to, what happened to, excuse me, we have 2 rounds. Let's say we have 2 rounds, so we double it. Again, we cannot, you know, do the 3 pig dead scenario. So we eliminate one of these. And in this case, we have 2 possibilities. Yeah, because there's always a possibility that two of them die. But I think like this is the logic. I don't know that I know how to generalize this very easily. And the reason why I'm trying to do it this way is try to figure out like the binary searchness. Um, like if I'm giving x pigs, how yeah for x rounds, how many what is the maximum for those pigs, and or maybe even a different way is given x rounds and k pigs, can do can I figure it out, right? And I don't know. This is a and maybe it's just like a one line silly problem. Oh, the other thing is that there are at most 1,000 buckets. Maybe it's something that we can abuse. Because I feel like if it was a easy formula, then maybe buckets would be higher. But I do wonder what this strategy is. I guess it's just something like, you know, like in theory, maybe we could extend this again, right? But then now you have to figure out how to do the math on the double one. So like maybe some of these will not be possible. Like the ones of two cannot be possible because the two ones we only have, because the reason is if you want to write it another way, BC and this BC, we have to differentiate these two and we only have one pix left, right? So that's basically why. So here we can write it this way because if only this one, and this one, like if only C is killed, we have these three things and you have two things to differentiate, right? So that allows us to do this. So that this is probably closer to the so this is still just one round, right? But here, knowing that we have a second round will allow us to do this. Oh man, I do not know how to do this. um, and then of course you have an additional round because now I'm just thinking one more round, right? So now I'm trying to think about an additional round. What do you do? Like this is for round is equal to 2, and then in that case, of course, now you can basically go. I mean, I didn't draw the entire branching, but you could kind of imagine like, maybe I can write this another way, but um, but if you give it an extra round, there's just more possible. There's just like more recursiony things, right? Let me see if I can figure out how to do. Like, I'm just figuring out something like, um, yeah. Well, I mean, I think we can brute force the answer really, well, because if this is very close to the max case. Well, let's put it another way, right? Put it another way is that if you're only given one round, and that's the worst case, because otherwise, if you're given most rounds, you can just do a lot. But if you're given one round, then the answer is going to be 10. So then that means that the answer is always going to be 0, or not 0, but well, from 1 to 10, right? And because if the answer is from 1 to 10, then we can maybe do some kind of crazy dynamic programming from this, right? Because okay, I'm gonna give it a try. I don't know that this is the right way. Feel free to speed it up or whatever, and kind of go for it. But let's say we have, this many picks and this many rounds left. Okay, let's just say picks and rounds. Then what happens? This is so annoying, isn't it? I don't even know how to construct this in a good way. don't think I know how to construct this in an easy way, but I would. Because the number of picks. Okay, so then let's say we have 3 picks in one round, then we would get this answer. I think maybe this isn't even right, to be honest. But this is 11 plus 8 is was it 19? So 3 picks, 2 rounds is 19. And I don't even know that this is the best strategy. So I think, yeah, as I always say, sometimes you get these problems and you're like, well, I'm just going to go home and, this interview is over. I'm going to go home. My interview clearly hates me or just having a rough day. And yeah, it is what it is. You take your L and go on. But how do I say this? So given one pick, I don't even know how to kind of write this in a reverse way. That's why I'm trying to think about it. So okay. So so these are binomial numbers, right? Because that means that in a 2 to the but I'm just trying to think, like, the hard part is that this is for round equals 2, right? If round is equal to 3, what do you do? I don't even know how to extend this logically, or like it's just the complexity tree is just way beyond what I can think about right now, right? I think what I would do is try to think. I don't even know. Because how do you even solve for round equals 3 using this logic in a consistent way, right? Because then now you have all this, sure. And the logic here is that, let's say we only get the C's, right? So then now you have 1 object and you have 2 things. But then how do you calculate for the fact that you have 2 rounds left, right? With 2 picks, right? Okay, so that means that, and it's not even, so it's almost like given X amount of picks or X amount of buckets, and I don't even know if this is right. So, like, what do the extra rounds buy me? Because because I'm trying to extend this to logic to 3 rounds, because then now the recursion is maybe the other way of thinking about it is maybe that okay, maybe another way of thinking about it, that's what I've been trying to do but not in a good way, is that okay, let's say I am given 19 buckets out this way. What if I have 20 buckets? Well, you go 0 to 8, so and then you know, maybe I don't know if this is a good thing, because then here we can say so what we're trying to do is figure out what is the weakest case, right? So okay, maybe this doesn't have to be a thing, but okay, so given X picks and 1 round left, I don't even know how to do this, but basically it's some like recursive thing where okay, let's see, okay, let's give it a temp. So okay, maybe in our base case then if rounds is equal to 0, if buckets is equal to 1, return true, else return false, or something like this. I don't know if this is quite what we want, but otherwise then what are we going to do? We're going to try to label for each picks but the thing is that I'm still doing it in a way I don't know how to extend this for rounds is equal to 3 in my head. Because you can use up 1 round, but I don't even know, because then now I'm basically simulating the pig logic, but I mean I guess we'll just have to figure it out. Okay, I don't know, because this isn't perfectly matches either, right? So but then in that case I really don't know this one. Maybe that's I don't know. Like I don't even know that this is the right strategy. I think that's the problem. Maybe I do need a hint, but I feel like I'm not that far off either. But let me see if I missed anything. I guess I don't think so though. Let alone if there's many more rounds. Well, so basically the idea is that okay, well, how do we distribute these in a good way? Well, we're going to greedily distribute if my scenario is correct, we're going to greedily distribute I feel like there's some square root thing as well, but maybe not. because with 4,000, right? So you have, let's say you're 2 to the 5th, so you have 2 to the 5th, which is equal to 32 buckets. And then now you have 32 of 32 buckets, but it's not quite that though, right? Like it's almost like the square root decomposition is what I'm thinking of, but then in that case, you can't just divide it out, because then because some pigs might just, like, if for example I mean it's the same thing logic of here, right? If we just naively do this, then all the pigs might die in 2 different bucket, but we don't know which bucket it is between those 2. I don't know that I know this one. This is is this the best way to do it? How do you even I think I'm just trying to figure out, like, how do you get this number, how do you get 5? Because or like the strategy, right? I really don't know. And I think, like, okay, how long have I been doing this? Been doing this for half an hour. How would you get this strategy that's 32, right? So let's say naively, let's just figure it out for a second. So now, yeah, the first 32, we just use the binary numbers, and then we get rid of the 1, 1, 5, so you don't have dupe. And then you have, was it 5 of them has 4s? That's just 5 choose 1 or something. 5 choose 4 as well. There's 5 ways of doing that. So then there's 26 left from this. And then was it how many 3s? That's not the right amount. It's 5 choose 3. So what's that? 5 factorial over 3 factorial over 2 factorial. So that's 5 times 4. So that's 10, right? So that's 16. Oops. And then this is 5 again, right? So that's 11. 2s. But this assumes that, the way that I'm doing it assumes that, assumes that we only have 1 round left, which is why this is a little bit off, right? Because, like, basically I'm just constructing this here, but with numbers instead of showing it out, because that's a lot of them. But maybe there's a more aggressive way, because we have more rounds. And I don't know how to mathematically construct that. Like, it may very well be that, okay, well, we can't have the 1 5s, but we can have more, right? Because here, this is where 4 picks die. Right, so there are 5 cases working backwards, right? But if we have 1 pick left, then you know, if we have 1 pick left and 3 rounds, then we could have 4, right? So, or like you can have 4 of them. Yeah. So that means that we can have 4 of these, maybe. So that's one scenario. Or like that's how we would break down these scenarios, right? But one, maybe that is the way to do it. But okay, let me say it again. So if we have 4 rounds, let's explicitly count in the rounds this time. Okay, so 32 has none, say. In this case, we have 31, 1, 5. If they're all dead, you can't really do anything. So, wait, why did I write it this way? Yeah, and then we repeat all the other ones. Is that right? No, let's write it. So the 4 picks dead scenario. What happens? Maybe that is the interesting one. Because okay, we know that in the original mix we have 1 5 pick dead, right? Okay. Let's say we have 4 picks dead. Maybe I'll write it away. 5 picks. 5 picks, it goes to 1, right? So we can, you know, initial one we can only do it once because otherwise game over, right? Let's say we have 4 picks. How do we? How many 4 pick combination there is, right? Well, 5 choose 4 is going to be. So there's 5 scenarios where this can happen because 5 choose 4, right? And then each of these, let's say one of them happened. So 5 choose 4 is going to be 5. Let's see, 4, you know, 5. And in each of these cases, if we have 3 rounds left and 1 peg, 3 rounds, 1 peg is going to be 4, right? So plus, so that means that it's going to be this plus 4 is the total number of buckets that this can support. Okay. 3 picks, what happens, right? So it's 5 choose 3. As we said, this is going to be 5 cases. Is that right? No, this is going to be 10 cases. Whoops. So 10 cases, and then you have 2 picks left, and 3 rounds. But this doesn't really give me what I need, I think. Oops, click on the wrong button. I did do it in the past. I don't know how to do it though. I don't remember this problem at all, obviously. Otherwise, I wouldn't spend 40 minutes on it. I mean, okay, right? So this is the part where I'm like trying to think about recursion. So then this allows us to kind of figure out how many things maximum, right? What does this 4 mean? This 4 means that we can have 4 of these, because in the worst case you can do this for 4. So that means that this should be times 4. But then this is now this times 2 picks left, 3 round strategy. Okay, maybe now we're getting somewhere. 2 picks is equal to 5 choose 2, which is against 5 times. So you kill 2 picks, you have 3 picks left, 3 round strategy, right? And then 1 pick is equal to 5 choose 1 is going to be 5 times. 5 choose 1 is going to be 5. Right? Did I mess this up? This should be 10 then. Oops. I think I just wrote it wrong here as well. 5 choose 2 is of course equals to 5 choose 3. That should have been obvious. But yeah, this is going to 4 picks left, 3 rounds, right? And then 0 picks is just equal to 5 choose 0, which is equal to 1 way or another. I don't know, sorry. Okay. So this is the max number of picks we can put in the first round. So maybe that's how we can optimize this. Man, past Larry must have been very smart. Current Larry, not so much. So okay, so we have picks and rounds. That's kind of what I was trying to go into. So okay, how many rounds or how many buckets can we support, right? So then now we have for okay, so let's say total is equal to 0. So for p in from picks plus 1 to be inclusive, again, if rounds is equal to 0, maybe if rounds is equal to 1. Okay, if rounds is equal to 1, then if we have x picks, then we can choose return picks plus 1, right? Because that's just, if we have 1 round left and we have 5 picks, then we can just put, we have to. Oh wait, no, that's not true, is it? My alarm is. If we have 1 round, then we could do the binary strategy. So this is wrong. Hang on. Right. So this is like so if we have 1 pick, we can do 2. If we have 2 picks, we can do 4, and so forth. Right. So right. Or I'll write it for the whatever people here. Okay. Right, okay. If we have 2 rounds, that's fine, right? Okay. And then now, maybe I could have done this, but I mean, I was just a little bit lazy about the grinding, I suppose, because I had this idea in my head. So, oh yeah, and if picks is equal to 0, we return 1 because you just, that's your case that you did here, because that's the only scenario that you can do it. So we're doing how many buckets can we support that has no picks left? Well, 1. It doesn't matter what round you're in, because yeah, okay. So in this case, we do combination of picks and p times go of picks minus p rounds minus 1. And then we return total. I don't know that this is right, but this is, I think, the logic that I have here, right? And then here we can maybe go something like for I in range of 20, it should be good enough though. If go of I rounds is greater than or equal to buckets, we return I. Otherwise, we just return 20. I don't know. I mean, it should be okay. And we might want to cache this. So, but for now, it should be okay. Let's just give it a spin. Okay. Wow, that was actually, I mean, I actually had this idea thought out, but I think I was missing this part of it. So I think, wow. Okay. Is this right? I think we need to do a little bit more testing, but maybe the way to do the testing is just to give it a submit. Wait, if rounds could be 0. Oh no, it has to be at least 1. Let's give it a quick submit, just because I'm a little bit lazy. I probably should have just put in more test cases, but oh wow, okay. And yeah, and of course, I actually, one mistake that I did make is that I should have cached this, to be honest, but because picks is at most like I said, it's going to be at most 10 or something like that. I guess this is like, you know, not that much, because also rounds is not that much, because at a certain point, this is going to be a big number. Is that even true? Yeah, because I think you just don't go that many rounds, but you should probably cache it if you have any questions. But I really should have done this a little bit faster now that I think about it, only because I was thinking about this entire way for a long time. So it wasn't like I wasn't thinking that, but I thought that I was trying to think of a easier way, and as you kind of saw, I finally just was going through, and then I just kind of type what I think is scenario, and this gives us the number of buckets to support, right? All right, let's see what I did last time. Oh man, this is a different way. Hey. Oh, this is much smarter than the way that I did it. I see what they're doing. I forgot about this actually. Yeah, wow, I am way sloppy today then. But I'm kind of also happy that, oh wow, this is a binary search. But what is the thing? Oh, I guess just given these rounds, find the last bucket. This is actually pretty cool too. But actually, I'm kind of happy that I did it this way today, just because it's something that's different, right? Like it might not be the easy answer, might not even be the great answer, but I did it a different way. Where the other way is actually more mathematical, and I hope that yeah, you go take a look into that. Yeah. Is that all I have to say? I mean, the complexity here is that this is only going to be 20, and rounds is at most like 100, but it doesn't even matter because if this is like 100, then like and pix is equal to 2, this would already return a huge number that it doesn't, it would just return after that. Maybe I could have cached it though still. I don't know that I could prove the complexity here. But yeah, but I think the other way to do it is just same idea-ish here, but instead of using this number of how many buckets we can support, we did it another way of just a base, which is that we have and we guess, okay, how many picks do we need, right? If we have one pig, then you just determine the number that it can support given these times, and then you just bucket it to the number of rounds. So, for example, if round is equal to 4, then you have 4 rounds, and then now you're just writing and you have 3 picks. Then this is just a base 3 number, and then you basically map each bucket this way, right? And then so then you bucket it not just across whatever, but across time as well. So I guess that's the way. But this is a very hard, weird problem. So yeah, let me know what you think. I think the other way is also cool, and I definitely was not thinking about that somehow because I don't know how to. And clearly did not duplicate it, but yeah, let me know what you think. That's all I have. Stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye. Oh yeah, stay tuned for the extra problem next. Bye bye.